Okay, these were examples of network covalent solids here. Because we got sp3 sigma bonds here, all of them. Over here, this is an example of network covalent solid as well. Within the plane, we have sp2 sigma bonds and pb pi bonds. But between these sheets, this would be an example of molecular solid because what holds these sheets together are intermolecular forces, IMFs. And so the solid's property depends a lot on what holds the particles together. In ionic solids, ionic bonds hold the particles together. Ionic bonds can be very strong or very, very, very strong, right? For magnesium oxide. Magnesium oxide, is it very soluble in water? No. To break apart that lattice would cost you a lot of energy, whereas sodium chloride you can dissolve. When we look at lattices, there's a regular repeating pattern. There's some long-range order to this. In fact, we can think of a lattice like this as being built up as smaller building blocks. These smaller building blocks are called the unit cell, and they're different shapes to the unit cell depending on how the atoms pack together. One of the most common shapes is a cube, but we could have these rectangular cubes, etc. Altogether, there are 7 different shapes found of these building blocks. Those are the 7 crystal systems. The most common shape that we encounter is a cube. And so this would be the building block here, or here, or there. And the atoms are different colors just to highlight it. And so here we could have the atoms arranged like in this fashion. This is called simple cubic. One thing about simple cubic is this huge gap. Do you see the huge gap inside there? Okay. So this is the first one we're going to build. There are actually only 3 shapes. Actually, I shouldn't call these shapes. There's only one shape, cube, and there are 3 different ways of arranging the atoms in that cube. And those 3 different ways are called the crystal lattice, Bravais lattice. Well, anyway, let's build this one. This is called the primitive cubic or the simple cubic. And so what you'll do is you'll get your model kit and look for the page marked simple cubic or primitive cubic, and it's going to tell you which plastic block to use, the half circle or the full circle. You can work with a partner if you want. And then it's going to tell you what letter template you should use. And for simple cubic, all you need is 4 rods. 4 rods where the circles appear on the template. The circled circle. Let's see. You want to put yours on the edges there of that square. We're only going to build one little cube, so on the shaded square.
This one's like broken.
Oh, that's okay. Just use it. Oh, make sure you have the half circle block. It's this one. I'm sorry? Primitive cubic. Put the rods on the little square. Oh, actually, that's put them on the corners of the shaded square. The rods. 4. You have to use the template though. What letter template are you going to use? A. Put 4 rods on the shaded square, and then put layer 1 is 4 clear colorless balls. Layer 2 is another 4 on top of that. so anyway, what the end result should look like is just like this. Are you getting something that looks like this? All right, the first thing is this the repeating building block? It turns out this is not. This is more than one building block. In order for the building blocks to stack one on top of each other, we have to slice the atoms in half. And so let me show you what I'm talking about here. This is the primitive cube. This is the actual building block. And so we stack one building block, it starts to build more of the atom. And so if you see this wedge here, this wedge is the wedge of the corner atom that fits within the cube. And so what we have to do is we have to slice the corner atom into 8 wedges. And so there's 1/8 of a corner atom at each corner. Now the blocks stack nicely. And so as we stack the blocks on top of each other and on the sides and underneath, we start to build the lattice. And one of the things we can calculate when we're looking at this is this. We can calculate how many complete atoms are inside this cube. And so if we have 8 corners, and each corner there's only 1/8 of an atom, then that means we can add up all the corner atoms and get one whole atom out of that. All the corner wedges. And so it turns out there's 1 atom per unit cell. There's something we can calculate easily. If we know we have 1 atom, what's the volume of that atom? The volume of the atom is 4/3 pi r cubed. So all we need is the radius. And then we can calculate the amount of space in this cube that's occupied by the atom. And then we can calculate the space or the volume of the cube. You know, the length here is 2 radii. And so we just get the length and cube it. And that gives us the volume. And so when we take the volume of occupied space over the total space, it comes out to a little over 50% packing efficiency. That is, it's about 50% occupied space, about 50% unoccupied space. The unoccupied space is that huge gap in the middle. Do you see the huge gap in the middle? That's called a cubic hole. It's surrounded by a cube of atoms. Now, that huge gap in the middle can fit smaller atoms. So try to put a green atom in the middle. If you put a green atom in the middle, then what you just built is the cesium chloride lattice. That is, the cesium ions fit in the cubic hole of a primitive cubic lattice of chloride ions. Cesium cations should be smaller than chloride, the anion. And so you can understand a lot of different crystals based on it turns out based on these 3 packing arrangements here. All right, go ahead and take that one apart. The next one we're going to build is this. This looks like cesium chloride. This one looks like just the one you had, right? Mm-hmm. But the difference between this and the one you had is the one you had a cesium, you had a cation in the middle, and then the anions around it. This one, all the atoms are the same size, because all the atoms are the same. Even though this one's colored red, it's colored red just for visibility. And so in a body-centered cubic, this would be like magnesium metal. Magnesium metal packs together in a body-centered cubic manner, and all the magnesium atoms are the same size. And so build the body-centered cubic lattice next. Body-centered cubic.